Hello everyone, Harry here. Welcome to Scrap Science. Bit of a different video today. I'm currently in the process of moving into a new lab space, so we don't have any practical experiments on the go right now, and also this is why there haven't been any videos for quite some time. While I'm in the process of moving, I thought this was the perfect opportunity to make a video that I've really wanted to make for really quite a long length of time. A more theoretical video to teach the core concepts of what my videos are normally based on, that being electrochemistry or electrolysis to perform chemical reactions. If you're here for the experimental side of things only, this video might not quite be the one for you because it's kind of all theory from here on in. But with that said, if you're keen, strap in because this is going to be quite a long one. We're going to cover all the basics about electrolysis that I can reasonably fit into one video. Additionally, I'll point out right now that this video is part of a collaboration I'm doing with another channel, Make It. He's been a massive help with the animations here. You'll see what I mean. I can't animate, so it's all Make It's doing. And he's got a channel full of theoretical videos on maths and science that you should definitely go and check out. Anyway, this intro has gone on for long enough, so let's get into our basic guide to electrolysis. To get properly into the ideas of practical electrolytic reactions, we need to take a big step back and look at something simple. In fact, we're going to start by completely removing the electrolytic cell from the discussion. Consider first a circuit involving a voltage source and a wire connecting the two terminals. The voltage source generates a potential difference between the two terminals, essentially a difference in potential energy of the electrons at the positive and negative terminals. Since the wire is conductive, electrons flow from the negative terminal to the positive terminal through the conductive wire, dissipating their energy as heat through the resistance of the wire as they flow. If we break the wire, electrons can no longer flow through the circuit, so that's kind of a boring thing to talk about. Instead, we can put other things in the circuit, an LED, a resistor, a motor, or whatever we want. The point I want to make is that no matter what we put in the circuit, electrons still have to flow around the circuit the same way as before. This gets a little bit confusing maybe if we put something in the circuit that doesn't conduct electrons, but can conduct different types of charges. Something like salty water, for instance. You'll probably be aware that water with salt dissolved in it is conductive. This conductivity isn't electron conductivity though, but instead a conductivity for the charged ions that are present in solution. Just like before, electrons still have to flow around the wires. They have to go through the wire up to the salt solution, and then more electrons have to come out the other side of the solution and go down the other wire to return to the voltage source. So the question arises then, what are the electrons doing such that they can flow up to the solution and then exit out the other side without flowing through the solution itself? The answer is that chemical reactions, or technically chemical half reactions, can happen on each of the wire solution interfaces. Chemical reactions that can either consume or generate electrons. In the interface where the electrons flow into the solution, we get a reaction or half reaction that consumes electrons, and on the other one, we get a reaction or half reaction that generates them so that they can continue flowing around the circuit. This is basically what's happening in every single electrolytic cell. So, now that we understand the overall process that's happening from the perspective of the circuit, we can talk about what's happening from the perspective of the electrolytic cell itself, our salt water solution. We're going to start by going step by step. First, our electrons come from the negative terminal of our voltage source and they react on our wire solution interface that I was talking about before. We're going to start calling this wire here an electrode. Even better, we're going to call it a cathode. We call it this because, as per physics and circuit theory convention, this is the name for any terminal of a circuit component where the electrons enter the device. On this cathode surface, our electrons are effectively being pushed into the solution by the voltage we've applied, and since they can't actually move through it, they will instead perform a chemical reaction, or half reaction, with something it finds on the surface of the cathode. By doing this, negative charge is transferred into the solution, and the mobile charges, or the ions, in the solution can now start carrying charge and completing the circuit. On the other side of the solution, we have our other electrode, the anode. Since negative charge is pouring into our solution from the cathode, it needs somewhere to go. Our voltage, once again, is essentially pushing our negative charge from the solution and into the anode. The only way charge can flow like this is with another chemical half reaction that can generate electrons and deposit them onto the anode. This occurs in such a way that the same quantity of charge is transferred on both the anode and the cathode. We shouldn't get any buildup. Anyway, now that we've got our electrons back into the wire, they can flow like they usually do and get all the way back to the voltage source. Two final points that I'd like to mention though. First, the discussion is exactly the same if, instead of being pushed away from the negative terminal of the voltage source, we consider that electrons are being pulled towards the positive terminal. Exactly the same thing happens and we get exactly the same result. Also, it's important to say that the chemical species generated on the cathode and the charge that's flowing away from the cathode is not generally going to be the same stuff that goes on to react on the anode. It's easy to fall into the trap of thinking that electrons are given to something on the cathode, then they zip right on over to the anode and give up their electrons again. Instead, the electron-consuming half reaction on the cathode, the overall flow of charge, and the electron-generating half reaction on the anode are usually three completely separate events, despite the fact that they're occurring simultaneously. And they can involve entirely different reactants and products. Hopefully that's simple enough so far. Now that we know how charge travels around the circuit, we can actually look at the electrode half reactions themselves. And for this, we might have quite a bit to get through. Okay, we said before that electrode half reactions are just half reactions that consume electrons on the cathode, or half reactions that generate electrons on the anode. Simplifying here, there are three main things that can happen. First, the electrode itself could be the participating chemical species. The surface of the cathode or anode could react chemically by the addition or removal of electrons. A common example is taking electrons away from copper when you use it as an anode. The metal itself dissolves as it loses electrons and transforms into ions. Next, the solvent of the electrolytic solution could be the reactant. In our case, water is generally our solvent. Examples here include transferring electrons to water like this, or taking them away like this. Finally, our half reactions can also involve the things that we have dissolved in solution. For example, we could transfer electrons to or from the ions in solution. A good example here is chloride ions. If we have these in solution, this is a possible anode half reaction, where we're taking electrons away from those chloride ions. And that's it, the three main types of half reactions that can occur on each electrode. We can transfer electrons to or from the electrode material itself, the solvent we're using, or the ions or molecules of the solute. On that note, we should probably start using the proper names for these half reactions. The half reactions in which electrons are given to a chemical reactant, happening on the cathode here, are called reduction half reactions. Reduction refers to the process of a chemical species gaining electrons. Likewise, the half reactions where electrons are taken away from a chemical reactant, happening on the anode, are called oxidation half reactions. Oxidation is the process of a chemical species losing electrons. We're going to use these proper names as we move forward. Now, this whole time that we've been talking about these electrode reactions that happen as a result of current flowing through our setup, I've been calling them half reactions, and you might wonder why they're given that name. It basically just boils down to the fact that you can't have just one of these half reactions going at any given time. For current to flow around and complete the circuit, you need a reduction half reaction to happen on the cathode and an oxidation half reaction to happen on the anode simultaneously. Since these two half reactions always come as a pair, we think of them performing a full reaction when combined together. And it gets even better. Since electrons are supplied by the cathode and consumed by the anode, we can combine our two half reaction equations for any given electrolytic process. The electrons on either side cancel out, and we are left with the full overall chemical reaction for what's happening in the solution as a whole. Basically, the halves combine to make the full reaction. As an example, if we perform electrolysis on water with sodium chloride dissolved in it, we've made an electrolytic cell that will perform the reduction of water to make hydrogen and hydroxide ions on the cathode, and also the oxidation of chloride to make chlorine on the anode. From a circuit current perspective, the flow of current through the solution is being mediated by negative ions moving this way, cathode to anode, and positive ions moving this way, anode to cathode. From a chemistry perspective, we can combine our two half reactions, cancel out the electrons, and we can see the overall process that's happening to the solution. We've now reached one of the most important things I wanted to talk about here. I've been talking about the electrolysis of salt water, and I've just told you which half reactions happen on each electrode. From a slightly oversimplistic perspective, the half reactions that occur during electrolysis of a given solution are actually easily predicted. Here, I'm going to introduce the table of standard reduction potentials. This is nothing more than just a list of reduction half reactions. The full list would be far too long to ever write down, so we simplify and include just some of the more common ones. The way things work out, you can also look at this table to find all of the oxidation half reactions, and to do that, you just flip all of the reactions back to front. To avoid confusion, I'm going to make the table a different color when we're looking at the oxidation version of the half reactions. So this is what it would look like when we're talking about the reduction half reactions, or the standard electrode potentials, and this is what it will look like when we're talking about the oxidation half reactions. It's red because oxidation is red in my mind. Don't argue with me on this. Now, the E0 value given next to every single reduction half reaction is also very important, and you'll notice that we've got them ordered from most positive to most negative. These values tell us how easy any given half reaction is. The higher the number, the easier it is to perform. Conversely, if we want to look at the oxidation half reactions, remember we do this by flipping all of the half reactions back to front, we also flip the negatives on the E0 values because everything is in reverse. So now we find the most positive values down the bottom of the list, and these are the easiest to do when we're performing oxidations. With one of these lists, it becomes really easy to figure out what happens on each electrode. On the cathode, we need to consider all of the possible reactants we have, which could be part of the electrode itself, the solvent, or anything in solution. Then we work our way down the list of reduction half reactions, starting with the easiest to do, and when the first one appears where the reactants are actually something we have available, that's the half reaction that will happen on that electrode. On the anode, simple enough, we just flip the half reactions back to front and work our way up the table instead of down. To get this into our heads, let's do an example. Consider we've set up an electrolytic cell using copper electrodes, and the solution we're electrolyzing is sodium chloride in water. The possible reactants on the electrodes here are copper from the electrode itself, water, the solvent, and sodium and chloride ions in solution. For the cathode half reaction, we work our way down the table, looking for the first half reaction that exclusively uses the reactants we have available to us. The first one we see here is the reduction of water, something we've already seen in this video. This is the half reaction that will happen on the cathode. We'll generate hydrogen and hydroxide ions here. Out of interest, the reduction of sodium ions to make sodium metal is also another possible cathode half reaction, but this is way down the list and could never happen when water is available for reduction. For the anode half reaction, we flip the half reaction equations and work our way up. Again, looking for the first half reaction that exclusively uses the reactants we have available. The first one we find is the oxidation of copper. This suggests that the copper will turn into copper ions on the anode, and that electrode will actually start dissolving as we run the cell. Again, out of interest, the oxidation of water and the oxidation of chloride ions are also possible half reactions, but they're too far up the list to happen here. So that's it. We know pretty much exactly what's going to happen when we electrolyze a solution of sodium chloride with copper electrodes. Hydrogen gas comes off the cathode, and the copper anode will start dissolving. Of course, as we do this, you may realize that the addition of hydroxide ions and copper ions into the solution may actually change the half reactions that occur as we continue passing current, because they make more half reactions available on our list. Or maybe they could react to form some kind of precipitate, but we're just looking at the basics here, so let's leave those possibilities alone. Right, that concludes the basics. We now know what an electrolytic cell is, how these chemical half reactions occur, and how to predict what's going to happen. There are exceptions and some extra considerations to think about, however, because this simple method of predicting which chemical half reactions will happen doesn't always yield the correct results. To understand why, we're going to need to start talking about some more complex ideas, starting with those values on the right-hand side of our table. These numbers are actually pretty important, much more important than I probably would have suggested before, and formally they're called the standard reduction potentials, or standard oxidation potentials when we flipped the table. You'll notice that these values are measured in volts, and if we think of voltage like a pressure that pushes the electrons around the circuit, this is kind of a measure of how much pressure, or how much electron pressure, or how much potential we need to push the electrons with in order to force them to react with the reactants and cause a reduction half reaction to occur. The higher the value, the less pressure is required. It's opposite to what you might expect, because you've got to remember that we're pushing negative charges around the circuit instead of positive ones. If we flip all of the reduction half reactions into oxidation half reactions and flip the negative on all of the E0 values, we can now think about the oxidation half reactions in exactly the same manner. In this case, the values are now the standard oxidation potentials, and they now measure the electron pressure or potential required to pull electrons out of our reactants and force an oxidation to occur. Again, the higher the value, the less pressure is required. Now, you might ask or wonder about the meaning of the 0 point in our little voltage scale we've got going on there. This actually means nothing at all, really. Due to the relative nature of potential, there's never really a true 0 volts in any context. Voltage is always a relative scale. We simply define the reaction of reducing hydrogen ions into hydrogen gas to be our arbitrary 0 volt point that we base everything else off. You can rationalize the idea of there not being a true 0 volts point by remembering that we can't just do one half reaction at a time. They always come as a reduction-oxidation pair. It's like if you're watching a tug-of-war tournament, you can't directly measure how hard each of the teams are pulling on the rope just by watching the games. Instead, you can only really measure from watching alone how much harder one team is pulling than the other team, because they're always pulling against each other in pairs. I don't know if this is making sense. Just by watching a tug-of-war game, you can't tell whether it's a situation where one team is pulling with 5 newtons and the other team is pulling with 10 newtons, or it's a situation where one team is pulling with 105 newtons and the other team is pulling with 110 newtons. So 0 newtons has no meaning when you're just watching a game of tug-of-war. This isn't making sense. So for our copper electrode electrolysis example before, we can now apply this knowledge. Remember that we found this reduction half reaction to happen and this oxidation half reaction to happen. Under these circumstances, we need to apply 0.83 volts of negative potential to push the electrons to do our cathode half reaction, and then an extra 0.34 volts to pull the electrons out of the copper for the anode half reaction. Overall, we're going to need to supply at least 1.17 volts to the cell to get the electrons moving and for this reaction to work. This is quite heavily oversimplified though. If you apply 1.17 volts to a cell like this, you won't really see anything happening. This is because I didn't give the full description of what a standard reduction potential is. Technically, the potentials associated with each reduction or oxidation half reaction tell us the potential that will allow the forward half reaction to occur at exactly the same rate as the reverse half reaction. So overall, no reaction occurs at the exact potential under standard conditions. If you push any given electrode to more negative potentials, the reduction half reaction is favored, and at more positive potentials, the reverse oxidation half reaction is favored instead. The more we push away from the standard potential, the faster the respective half reaction gets. The extra potential we need to apply to get a half reaction going at a reasonable rate is called the overpotential. The more overpotential, the faster the half reaction, but the more energy is lost to heat as current flows. So, once again, back to our copper electrode electrolysis. 1.17 volts is our calculated potential under standard conditions, but to get the reaction going, we're going to need to apply more than that. It gets more complicated even because we are not working under standard conditions. The potentials of the half reactions do change quite significantly depending on the temperature and the concentrations of the reactants and products. We can calculate the real potentials under our particular conditions using the Nernst equation, but maybe we'll leave it there. That's not too important in our examples so far. Now that we've looked at all that, there are just a couple of final things I'd like to mention. The first of which being one of the major limitations to what we can do and which reactions we can perform with electrolysis. This limitation I'm referring to actually comes from the fact that we're normally using water as the solvent for our reactions. If we wanted to do, say, a reduction that requires more negative potentials than the reduction of water, the reduction of sodium ions, for example, we just can't do it because the ever-present water will always be easier to reduce. The same goes for oxidations. If our oxidation half reaction is more difficult than the oxidation of water, the oxidation of fluoride ions, for example, we just won't be able to do it. The limitation of water kind of leaves us with a window of potentials, actually named the electrochemical window, that we can actually do half reactions within. Under some circumstances, you can go a little beyond the electrochemical window of water, but the further out you go, the more difficult and less efficient it becomes. To get to those far off half reactions, we need to use a solvent with a wider electrochemical window, or we could ditch the solvent entirely and electrolyze molten ionic salts. In liquid form, the ions in salts are mobile, so electrolysis is extremely effective and there are no issues of the solvent reacting preferentially. For example, electrolysis of molten sodium hydroxide directly reduces sodium ions to sodium metal and oxidizes hydroxide ions to steam and oxygen gas. Anyway, back to water. Another limitation of aqueous electrolysis occurs when our products of the electrolytic reaction go into solution. If our products are gases that leave the cell, or some kind of product that adheres to an electrode, this isn't generally an issue. But when we make soluble products, the oxidized or reduced species can migrate to the opposite electrode and do the exact opposite half reaction, meaning that we've achieved nothing overall. Sometimes this is useful, such as in plating experiments, where we dissolve a metal from the anode and reduce it on the cathode to make a thin metal coating. However, it's much less good when we're doing something like oxidizing bromide ions to hyperbromite. If we were to do this, a lot of the hyperbromite we generate as an oxidation product on the anode is going to travel back over to the cathode through diffusion, through the solution, and get reduced back to bromide. There are a couple of ways to solve a problem like this, but one of the main ones is to set up a divider between the cathode and anode to keep the electrode products separate. A fine porous diaphragm or an ion exchange membrane between the electrodes would allow ions to be pulled through it by the electric field, but would greatly limit the amount of mixing and diffusion that can naturally occur between the cathode and anode. In our hyperbromite production example, the hyperbromite ions would, in a divided cell, get generated much more efficiently because they can no longer diffuse towards the cathode. In fact, the direction of the electric field also keeps the product from diffusing away from the anode compartment in this case. I have used this kind of separation before a few times myself. For example, in my video on oxidizing ammonia to nitrate, I used a paper separator to prevent the nitrate ions from migrating to the cathode and getting reduced. On the note of keeping the anode and the cathode separate, there's another effect resulting from aqueous electrolysis that we can take advantage of. Think about our two fundamental half reactions that involve water itself: reduction to give hydrogen and oxidation to give oxygen. If we look closely at these half reactions, we can see that the reduction actually generates hydroxide ions or destroys hydrogen ions, and the oxidation generates hydrogen ions or destroys hydroxide ions. As a result, when we get one of these half reactions going, we generate increasingly acidic conditions on the anode and increasingly basic conditions on the cathode. Without a separator, these effects kind of cancel each other out, but separating these two products allows us to actually accumulate acids and bases when we run reactions involving water. This forms the basis of the chlor-alkali industry, along with a few of my older videos. With an overview of the practical components of electrolysis now kind of complete, it's time to look at the maths. Luckily, there's not too much maths to understand for this basic intro, provided you've come into this with a good knowledge of stoichiometry and balancing reactions and things like that. Early high school chemistry, this should be easy. If you look at a particular electrode half reaction, the oxidation of water to give you oxygen gas, for instance, it should be obvious that to make 1 mole of oxygen gas, we need 4 moles of electrons to pass through the cell for the half reaction. The question is, what do 4 moles of electrons look like? It's not too tricky to figure out. We just need some way to convert between moles of electrons and our standard unit of charge, the coulomb. As it happens, there are 96,485 coulombs of electrons in 1 mole of electrons. This is the Faraday constant. If we ever need to work out how much charge we need to pass for a reaction, we just need to know how many moles of electrons we need, 4 in our example before, and multiply that number by 96,485 to get the number of coulombs we need. In our case, we need 385,940 coulombs to get a mole of oxygen gas. And then a little recap, charge is just current multiplied by time. So if we were able to run, for example, 8 amps through our electrolytic cell in this hypothetical scenario, we just need to divide our charge by 8 to get the time in seconds. In this case, if we were to run 8 amps through a setup that does this half reaction on the anode, that's about 48,000 seconds or 13.5 hours to make a mole of oxygen gas. And that kind of brings us to the end of everything we need to know here. That is the basic guide to everything I think is important to understand in the fundamentals of using electrolysis to perform a chemical reaction or some kind of synthesis. To finish off the discussion though, we probably need to complete the story. And for that, we need to go back to our discussion where we figured out the necessary voltage to get a reaction to go ahead. We've done a couple of reactions where we looked at the electrode potential of the reduction on the cathode, combined it with the potential of the oxidation on the anode, and we got the overall required potential for the cell as a negative value. This is, again, basically telling us how much potential we need in order to push the electrons to transfer between the electrodes and the reactants. However, it is perfectly possible to pick a pair of half reactions that would give us a positive value here. The oxidation half reaction just needs to be below the reduction half reaction for this to work out. For example, the reduction of copper ions to copper metal and the oxidation of zinc metal to zinc ions. Performing our analysis of this overall reaction would give us a positive value. This means that we don't actually need to apply a potential and push on the electrons to enable the transfer. The electrons actually push themselves and the reaction is spontaneous. We don't need a power source, just shorting the cell will allow current to flow. Of course, spontaneous reactions have to be treated a little differently when dealing with practical setups. If we have our reactants in solution or on the electrodes, allowing them to mix together will just cause the reaction to happen then and there. We won't extract any voltage or current from it. In these cases, it's essential that we actually separate the two half reactions with a divider, such as the ones we talked about before. That way, electron transfer can only occur through the external circuit, allowing us to draw a voltage and power things with it. As you may have guessed, or known, we're basically describing a battery, an electrochemical cell. I'm not going to go into any more detail here because this little tangent is really just here to complete the discussion. We came here to talk about electrolytic cells, after all. Instead, I'll encourage this as a kind of final exercise for the viewer. You should be able to, now with all of your expert electrochemistry knowledge, look up various battery chemistries and the half reactions within and predict the theoretical voltage you should get from such a cell. If you've made it this far, I sincerely hope that you've enjoyed the video. It was a lot of effort to make. I did enjoy putting it together, but it will be nice to go back to some proper chemistry demonstrations in our next few videos. I will say again, big thank you to Make It, who put together all of those overlaid animations. You should definitely go and check out his channel. Links in the description, of course. He's been a massive help here. Let me know as well if you'd like to see more theory-based videos in the future. There's a lot more to say here, and I could probably make a whole bunch more videos of a similar length about the theory of electrochemistry if there were an appetite for going really in depth. Last of all, some people have been asking me for quite some time to start a scrap science Discord server. I've done that, so go down to the description, find the link, join it. I'll see you there. Or not, I don't care. I don't know much about Discord, so I guess I'll learn fast. See you later.